Thanks everyone for coming to this morning CHEP seminar. We're very fortunate to have Brian Kovac joining us from Carnegie Mellon University. He's an associate professor of economics and public policy, who does research in the area of international migration and trade. He's published in leading journals in the profession, including the American Economic Review, the Review of Economics and Statistics, the Journal of Monetary Economics, American Economic Journal Applied, Journal of International Economics, and countless others. And we're very excited to have him here today to present maybe some groundbreaking work methodologically on understanding migration responses to local shocks. Brian, thanks so much for being here.
It's absolutely my pleasure. Can you hear me okay?
Yes, we hear you just fine.
Great. Well, I really appreciate the opportunity to present today and for the flexibility to do so online. I hope to have the opportunity to meet you all in person sometime soon. I'm fortunate to be collaborating on this project with Kirill Borusiak from University College London and Rafael Dix-Carneiro of Duke. And we are actively working on this, so your feedback will be particularly valuable. I would encourage you to just jump in with questions, unmute yourself and ask a question. On Zoom, that often ends up with us talking over each other for a moment, but that's just fine. I'd like to get your feedback on this. So I've spent many years studying spatially heterogeneous effects of various local labor demand shocks, some coming from trade liberalization, some coming from elsewhere. And in many cases, we find that a given policy change caused wages or employment probabilities to grow or contract a lot more in some places than others. And that raises the question of why workers don't just leave the relatively negatively affected places and move toward the relatively positively affected places. Understanding these migration responses to local shocks, or the lack thereof, is important to understand the impacts on welfare, regional inequality, between group inequality, to explain the persistence of some of these effects, and to inform potential policy responses. So the conventional approach to trying to understand how migration responds to local labor demand shocks is to estimate a regression like the one shown on this slide, which regresses the proportional change in a location's population on hopefully exogenous local labor demand shocks. We're going to be using the trade economists' convention of hats representing proportional changes in this talk. There may be one counterexample that I will point out, but hats here don't mean estimates, they mean proportional changes. So many papers estimate this kind of regression. This is not a complete list, there are many more. And in spite of finding substantial effects on local labor market outcomes like wages and employment, they often find little migration response, as they infer from finding an estimate of this coefficient beta that's close to 0. So that's a bit surprising. Just to point this out, I am one of the people who've run these regressions. You can see my name here a few times, and I've often found this confusing. Why don't we seem to see migration responses when we find pretty substantial differences in the effects of these shocks across locations? So how can one interpret an estimate of beta that's close to 0? Does it mean that migration is prohibitively costly and so people don't respond? Does it mean that location choices just don't respond much to changes in local wages or employment probabilities, so the migration elasticity is low? And how should we use these estimates? Can we use beta from this conventional migration regression to evaluate local population responses to the observed shocks? I think that's what most of us think we can do when running a reduced form regression like this. Can we use them to predict local population responses to counterfactual shocks? And if beta is close to 0, can we just ignore migration when studying other regional outcomes or when building quantitative models? In this paper, we'll develop a theoretical framework in which to interpret beta from the conventional migration regression. And we'll find that most standard interpretations are quite problematic. In fact, you can find an estimate of beta that's close to 0, so it looks as if population doesn't respond, even when the observed shocks drove substantial spatial reallocation of people across places, when workers are in fact highly responsive to local economic conditions, and when responses to counterfactual shocks would be quite large. And And because of these problems in interpreting the results of this conventional regression, we'll propose a simple alternative procedure that's better suited to answering questions like this. So we'll formalize everything as we go through the talk, but the intuition behind everything we'll talk about today, I think, is pretty straightforward. The main problem is that the conventional migration regression is misspecified due to the bilateral nature of migration. The population in a given location L changes not just depending on the shock to that location, but on how that shock compares to the shocks facing other locations that people might go to or come from with respect to location L. And this misspecification leads to very poor predictions of the effects of the observed shock because it doesn't account for the important information on shocks to other relevant locations.
Right, can I ask a quick question?
Please.
So, so if we were thinking about a traditional gravity equation where you can control both the destination and original characteristics, I'm thinking about how much of that would address some of the problems here that you raised.
The reason that that doesn't work well in this context is that you can estimate a gravity equation when you have shocks that are at the source destination level. So gravity equations are good at estimating changes in things like trade costs between locations. Now, we're going to have a gravity style model that's taken directly from the trade literature in this paper. So the reason that we're not using that kind of standard gravity framework with fixed effects for sources and fixed effects for destinations is because we're interested in labor demand shocks that operate at the location level. Okay, if we wanted to study observable changes in migration costs, maybe say we're building roads between locations, then that more traditional trade approach would be exactly right for us. All of that said, though, you're on exactly the right track. The modeling framework we're going to use is, at least the production side is exactly the same as those frameworks. It's a good question. Okay, so we have misspecification because the conventional regression is misspecified because it doesn't include information on the relevant shocks to other locations. This misspecification is going to have a bigger impact when shocks are spatially correlated. As an extreme example, imagine that all locations get the same shock. Then there's no incentive to move because the same thing has happened everywhere. So I'll be in a location, maybe I got a bad shock, but if I look around and all my other potential destinations got the same bad shock, there's no incentive for me to move. And then you would find a beta of 0, but we haven't learned anything about how mobile people are in response to differences in economic conditions in different locations because those shocks were so correlated. So this is a situation where a shock to L might induce very substantial outmigration if you only shock that one place, but when you have correlated shocks across places, you find a migration estimate that's very close to 0. Things will be even worse when cross-industry mobility is also costly. National shocks to industries or sectors that are used in shift share style regressions we'll find don't induce much migration. And the intuition behind that is that if I'm stuck in an industry because of very large industry switching costs, then there's very little incentive for me to move between differently shocked locations because I'm still going to be stuck in that same industry facing that same shock. So I could move from the steel industry in Pittsburgh to the steel industry in Scranton, Pennsylvania, but things aren't going to improve much because I'm still stuck in that same industry facing the same shock. And what we'll find is that these problems can be solved by redefining regional treatment. We say roughly here, we have a literal approximation that yields this result. So approximately, the shock to location L minus the average shock facing relevant origins and destinations will be approximately what drives changes in local population. And we'll define how this average is constructed and what relevant origins and destinations are as we move forward. So we're going to build a theory model that has costly migration between local labor markets. We'll use that to interpret the conventional regression estimate and then use the model to get a model consistent solution. We'll then extend the model to include costly mobility across both locations and industries, and then do some Monte Carlo simulations to try to see quantitatively how important the problems are that we'll be able to see in the theoretical analysis. So as I mentioned already, a very large literature runs these regressions spanning labor, development, international, urban, et cetera. This is a very small fraction of the papers that actually run these regressions that I'm showing you on this slide, but you can see that they're used in many different contexts, thinking about traditional Bartik shocks, trade shocks, as in some of my work, or resource questions like with exposure to shale gas, droughts, commodity prices, or the Great Recession. Some folks use these estimates to make modeling choices. Specifically, a few papers have justified omitting the migration channel from quantitative models because so many of these papers find a regression estimate that's close to zero. There are a few empirical papers that intuited the problem that we're going to try and solve formally today by putting in some ad hoc controls for spillovers. And we'll see that they're actually fairly similar to what the model suggests, so we can rationalize and refine those approaches. We're going to use a standard static gravity model that's been developed in the trade literature and used in the cited papers here to study location choices or commuting. And we also do our work is kind of in the spirit of these papers we've cited here, looking at reduced form estimation in a setting where there are general equilibrium spillovers. So if there aren't any questions about the big picture, I'll jump into the model. Okay.
So I just have one quick question in terms of, I guess, how you're defining a local shocks, because it sounds like, you know, a lot of the problems with this literature are local shocks are not actually local. So is there kind of a, you know, a spectrum of, you know, national shock to local, and what you're kind of focusing on is what's in between that, or is it something different?
Yeah, that's a great point. So you're right that there is a sense in which sort of the level of aggregation that a paper uses might influence the problems that we're describing today. We're going to assume the best case scenario for this empirical exercise, meaning we assume the existence of exogenous local shocks. And those shocks may be correlated across different locations. But even with, we'll define exogeneity in this context carefully, but even with a sort of perfect exogeneity, all the problems that I just described are present. So even if you've got an exogenous shock, then you're still in trouble. Now, what might be possible is to aggregate up to the point where all of the correlation between locations is subsumed within each aggregate location. Okay, so that is possible in some cases, like maybe the shale gas case. If you could partition the United States into places that are on sort of different shale formations, then maybe you wouldn't have correlations between them. Forgive me for not being an expert on shale gas, but that's sort of a general idea that might work. Because the vast majority of these papers use shift share style shocks, they're going to be inherently correlated across all locations all the time, because almost all industries are present in almost all locations, at least to some small degree. So, you know, an industry shift share is a weighted average of these industry shocks. And so, you know, if the, you know, electrical equipment industry is present at all in all of these locations, then you're gonna inherently have correlated shocks. So you probably can't aggregate your way out of that sort of issue. But you do make a good point, though, that for some regional shocks, you might be able to aggregate yourself, if not entirely, at least somewhat out of the problems that we're describing. That's a good point. Okay. So our goal in building this model is to derive clear and intuitive expressions for how local labor demand shocks affect local populations in the presence of costly migration. We'll see why the costly migration is important. We're going to try to avoid cluttering the model with other potentially interesting and important mechanisms such as housing or capital markets. We're really trying to make the point to and give you intuition for the problems rather than having a full-on quantitative model with every mechanism that you might be interested in. So it's going to be intentionally simple. We'll have many local labor markets indexed by L, producing in many industries indexed by N. We'll use a multi-sector Armington framework for those that don't do international trade. What that means is simply that within a given industry, goods are differentiated across locations. Okay, so in a particular industry, each, say, city or county produces a different variety of that industry, and consumers have a love of variety across those different versions. Preferences will be CES across varieties, hence love of variety, and Cobb Douglas across industries. We'll assume competitive input and output markets. For simplicity, we're going to make a small country assumption so that the industry price index is set on the world market. That gives us a way to shock industry prices very easily in the analysis. We'll assume, for simplicity, again, homogeneous labor with inelastic labor supply to any sector. Their labor supply to a given location depends on a location choice that we'll describe shortly. Agents are myopic in that they care only about the current period, but they do know equilibrium wages across locations. So they're not surprised when they move to a location and get a different wage than they expected. And we're going to consider standard comparative statics, where we consider small shocks perturbing a steady state. Okay, so feel free to guide me on how much detail to go through on the details of the model here. I'll go quickly, and then feel free to ask questions if you'd like more. As I said a moment ago, utility is Cobb-Douglas across industries and CES across varieties within industry. Note that because we've got a small country here and we're thinking about an open economy, consumers can consume varieties produced from locations within their country, but also from locations in the large outside world. This gives you a standard CES demand bundle. Prices here are determined by marginal costs because it's a competitive labor market. And the marginal cost is determined by the local wage and potentially heterogeneous productivity terms at the industry region level. The important thing about this structure is that it gets us a very nice expression for regional labor demand. Labor demand in a region L has a constant elasticity of labor demand, constant wage elasticity of labor demand with the wage W. And there are these demand shifters D, which we'll be able to change to think about local labor demand shocks. Okay, so we'll be changing D to shift these demand curves around and be able to analyze changes in labor demand across locations. Okay, so that's the labor demand side. On the labor supply side, we have a standard location choice, a discrete choice model, where workers consider the real wage in a potential destination D. They face a moving cost given by the log of tau. Those moving costs can be arbitrary for all pairs of source destination. And they face a type 1 extreme value shock, idiosyncratic shock at the individual level across destinations. And as this parameter theta gets larger, the variation in those shocks gets smaller. So the reason we use this kind of formulation and the great idea from McFadden is that this particular sort of error distribution gives you nice closed form location choice probabilities given by pi. So the probability that someone in L chooses location D is pi LD here. What you can see is that theta is the migration elasticity, which captures how relative wage changes affect relative location choice probabilities. And the less variation that there is in those idiosyncratic shocks, the bigger is theta, the more responsive people will be to local wages, because there's less variation in this idiosyncratic term, and so the wages matter more for their location choices. Okay, so that's what theta will mean, and that'll be very important for us. So you can take these pi's and the initial distribution of workers across locations L, and then just aggregate up to see how many people in total choose location D. Okay, so we've got L0 people in each location, pi LD of them choose destination D, sum that up across all sources, and you get the number of people that end up in location D.
Sorry,
Please.
is industries or location preference tied into this idiosyncratic? Can we understand it that way?
Okay, great point. I didn't say something important, so thank you for asking. Right now, we only have frictions across locations. Okay, so we're starting with the simple model that only has location frictions, and about halfway through the talk, I'll generalize to a model that has frictions in both industry and location dimensions. Okay, so right now, everything is at the location level. Thank you for pointing that out. The intuition's a little simpler here, so that's why we do the simpler version first. As I mentioned, we're going to think about small changes so that x hat is defined as the proportional change in x, which for small changes is the same as the change in log x. We can write that regional labor demand expression in matrix notation like this, but this is just that same isoelastic labor demand curve. Regional labor supply that we saw on the previous slide looks like this. It's important to note that this matrix, capital pi, just consists of all the little pi's. Okay, so those shares of people from origin O choosing destination D. And then we have a similar matrix, gamma, which we call the in-migration shares. It's the share of people in location D who came from origin O. And then when you solve these two matrix expressions simultaneously, you can substitute out the wage changes, and you end up with the effect of labor demand shocks on the number of workers in each location. And you can already see an important consequence here that deviates from the conventional migration regression. The change in location and the change in population in a given place depends on the shocks to all of the places if they're connected through migration. Okay, so you can already kind of see that misspecification where we need to know things about all of the shocks to figure out what happens in this location, not just the shock that hits this location directly. Now, all of those changes on the previous slide are counterfactuals relative to a no shock world. Okay, so all those changes mean, how would the population be different if we got hit with a shock D hat versus if we got hit with no shocks? Now, we can't observe that counterfactual world in the same time period, of course. So we'll make a steady state assumption that equates counterfactual changes and observed changes relative to the pre-shock period. The idea is that if the system is at steady state and you don't shock it, then nothing will change. And so any changes that we observe during the pre-shock period, where hopefully there are no large shocks affecting the data, can reveal the patterns of behavior that we would have seen in the absence of the shock. So we'll use the pre-shock information to reveal this baseline or steady state set of migration shares, these pi zeros and gamma zeros, and L zeros. We'll also assume, very optimistically, that our empirical analysis observes an as good as random demand shifter Z hat, where the total change in labor demand in a given location has an observable component Z, that's what the econometrician gets to see, and then unobservable components zeta, such that Z is mean independent of the vector of zetas, and that mean is the same for all locations. Okay, now, what does this all mean for us? Normally, when a person makes a heroic orthogonality assumption, you should be concerned. But because of the nature of this paper, it's the opposite. What we're saying is we're going to give you the best case scenario for these regressions and assume that these shocks are as good as random with respect to unobserved changes. And we're still going to have all the problems that I told you about at the beginning. Okay, so this is on top of any exogeneity concerns or endogeneity concerns. Okay, does that make sense? Great. So now that we've said we have an observed shock that may not capture all of the changes in labor supply and labor demand affecting these locations, the population response to observed shocks looks the same as the expression we saw previously, except now it's got this error term zeta 2, okay, which is just a simple function of zeta 1 from the previous slide. So this is basically the result of the model that we need. If you give a vector of shocks, baseline mobility between locations in the gamma and pi matrices, and we know this parameter, or this ratio of parameters, theta over sigma, then I can tell you what the model would predict for changes in populations across locations. But this expression isn't particularly intuitive, at least not to me. And so what we derive in the paper is an approximation under low mobility, where gamma and pi approach the identity matrix. And this yields what I think is really helpful intuition for what's happening in this more general expression. So what's that intuition? Well, first, for a given set of shocks, the effect on local populations will be larger when the migration elasticity is higher. That makes sense when people are more responsive to changes in economic conditions, and when labor demand is less elastic. The reason that that makes sense is that if you picture a downward sloping labor demand curve, the steeper it is, the more a shift to the right will change wages. Okay, so if you have a really flat one, then wages don't change very much. If you have a really steep one, then wages change a lot. Okay, so less elastic labor demand curves get you larger responses to a given shift in the demand curve. Okay, so that's this first term. We also see that there'll be a larger effect when this location has a larger baseline migration intensity, meaning the share of the population that are migrants, either in or out in steady state they balance, is larger. Then it means that that's a place that has relatively low mobility costs to a bunch of other relevant locations. And so they're going to have larger effects of a given shock. And then perhaps most importantly, we see that what matters isn't the shock to this location L, but it's this location shock compared to other locations shocks. That's what we mean by minus L, where those other location shocks are an average of shocks across locations not equal to L, with the weights given by the importance of those other locations in baseline migration flows into or out of L. Okay, so this is just the average flow between K and L in the pre-shock period. This is the total number of migrants into or out of L in the pre-shock period. So places that are more connected through the initial migration flows will get more weight here. Okay, so if you want to choose a tangible example, I'm sure that lots more people migrate between San Diego and Los Angeles than migrate between Pittsburgh and San Diego. And so in that case, if you're thinking about shocks hitting San Diego L, then what's going to matter a lot for how San Diego's population changes in response to a shock will be Los Angeles's shock, much less so Pittsburgh's shock, because it'll get a lot less weight in this weighted average. Okay, is that clear? Great.
So maybe this is not a good, metaphor or something. It sounds like it's the multilateral resistance term that we have in trade literature has some similar flavor here. Is that right?
Yes. Yeah. That's exactly right. I'll need to think a little bit more carefully in that dimension, but yes is the answer. There may be implications I'm not thinking, but it is similar. Okay, so can you remind me, Young, we go until we have like 45 minutes left, right? A little less. Okay, great. Okay, so given this model and our understanding of how shocks should actually affect local populations under the assumptions of the simple model with bilateral migration costs, we want to think about what beta means. Was there a question?
Yeah, sorry, it's me. Just so I'm getting my head around kind of the interpretation of this, right? So this isn't an omitted shock that's, different shock that's happening to an alternate jurisdiction, but just how sort of relatively how this is affecting jurisdictions that might differentially sort of affect flows, given the example we just gave. Is that how I should be thinking about this?
I'm not sure, so let me try to say it a different way and see if we converge. There are a vector of shock values across locations. So if you want to use the shale gas example, there are some places that are on top of shale gas that are going to be very affected. There are some places that have a little bit of shale gas and maybe will be minimally affected. And then there are places that are nowhere near shale gas and won't be affected at all. So that gives you the value of Z hat across all those different locations. And then to understand how that might affect population flows in a particular place, you'd need to know how exposed is this place to shale gas in comparison to how its migration connected locations are exposed to shale gas on average.
Yeah, that's helpful to me to sort of think, I'm thinking about sort of a similar shock kind of differentially affecting these areas rather than some omitted other shock. Thank you very much.
Okay, now I understand what you mean. Yes, okay, so the omitted shocks are all in this zeta term, and we've assumed that the local shocks are orthogonal to that set of unobserved shocks. So any changes in labels
this is back to the shock actually being exogenous and still the problem.
You got it exactly right. Yep. Yeah, and you definitely need to worry about that. So I'm not trying to downplay it, but we want to highlight a separate issue. Okay, so what does it mean to run this conventional this conventional migration regression in the context of the model? So the theoretical heavy lift in the paper is theorem 1, which shows that under that intuitive low mobility approximation, and for the sake of understandability with homoscedastic shocks, the appendix does show you the result for heteroscedastic shocks, and all the conclusions are the same, but it is a little harder to talk about. So we're going to do homoscedastic shocks for now. What we find is that beta captures that ratio of parameters times 2, just like in the model. But then instead of the location-specific migration intensity, it has this term, which is the national migration intensity. Okay, so you could think of that as a population-weighted average of migration intensities across locations. In the denominator here is a bit of a nuisance term, which is a placebo kind of national migrant share in a world where the steady state distribution of population comes from a model with no migration costs. Okay, so this is saying what share of the population do we think would be migrants in a world with no migration costs? And when everyone's drawing idiosyncratic location-specific terms every period from that type 1 extreme value distribution, almost everybody's going to move, because almost everyone is going to get a draw that's a maximum draw that's different from the one they got last period. Okay, so this term, that's a long-winded way of saying that this term is approximately equal to 1. And so for the sake of the talk, we're going to ignore it, okay, because it's very close to 1 in practice. Importantly, this regression estimate contains what we're going to call the attenuation factor. And this is an object that's below 1 when shocks are particularly strongly correlated between migrant-connected locations. And this captures that intuition I told you at the very beginning, that if all the places you might consider moving get hit with the same shock, then there's really not much reason for you to move. Okay, because you're not going to improve your situation by moving to any of those places. So to make this a little more formal, what is rho in this attenuation factor? It's the migrant flow weighted shock correlation between origins and destinations. Okay, so take all origins and destinations in the country, take the flow of migrants between that origin destination pair as a share of all the migrants. So that generates your weight, and then see what that correlation between that origin and destination might be. Okay, so this just tells you how correlated are shocks across space, across migrant connected space. And then in the denominator, we have another one of these nuisance terms, rho tilde, which is the same thing, but in a world with no migration costs. And I can go into some more detail here if you'd like, but in a world with no migration costs, people move between places proportionally to their size. And so when throughout the talk I say correlated shocks between migrant connected locations, what I really mean is a high correlation between migrant connected locations, more so than you would expect given their sizes. Okay, and here you can start to see a bunch of gravity-like intuition coming through. Yeah. Okay. So this is what's in beta, and now we're going to compare what beta gives us to what the model says is true. And it's important to note that the regression coefficient beta can be small for any of these reasons, because it's very attenuated because of highly correlated shocks, because there's not a lot of migration in the economy, or because the migration elasticity is genuinely close to 0. But what you can see here is that finding a beta close to 0 by no means means that people aren't responsive to shocks. Theta could be huge. People could be very responsive. But if you have very correlated shocks, this attenuation factor is going to pull beta way down close to 0. Okay, so this is the operationalization of that intuition we had on slide 4 or 5. So now we're going to go through some standard interpretations of these regression coefficients and see what we can and can't learn. We're going to start with what we cannot learn, but I will tell you something positive in a few minutes. I've just rewritten the decomposition for beta that we just described. Here's the true model-based change in population. And we may not get into this in the interest of time, but in case people want to read this on the slides, we've got this notation where we take a vector z hat and we replace its lth element with the scalar a. Okay, so this means taking the z hat vector and then replacing the lth element with the scalar a. Okay, and that lets us think carefully about some of these counterfactuals that we're going to use to interpret beta. So the most common interpretation of beta, I just went back through like 70 papers in the last 3 days, and almost all of them that run this regression, including a few of my own, interpret beta as the effect of shocking one region by some convenient shock, and the most convenient one is 1. So beta is not the effect of shocking one region by 1. How can we see that? Well, the true change is given by the model when facing a vector of zeros, compared to the model when shocking that one place with a vector with a shock of 1. Okay, just shocking the one place with a vector of 1. Sorry, I misspoke. And what do you get when you plug those things in and subtract? Well, you get 2 theta over sigma times the local migration intensity. Okay, so that's the true population change in that shocked region under the model. What does the model predict? Well, it predicts beta times 1, which is beta. Excuse me, what does the regression predict? It predicts beta times 1. You get this parameter term that matches, but then you've got the national migration intensity. And as we'll see in practice, that can differ a lot from the migration intensity in particular locations. And so you might be having a poor prediction because of that. And then you've got this potentially substantial attenuation term that will pull beta much closer to 0 than the true effect of shocking one region. So the problem is that the regression-based prediction omits location-specific migration intensity, and it suffers from attenuation. You get identical conclusions for other interpretations involving changing the shock to one location. So you might think, well, Brian, of course this doesn't work. It's a counterfactual shock. This is a reduced form regression. Well, you can interpret it the effect of the observed shock in location L. So beta times z hat L. That will be wrong for exactly the same reasons in exactly the same way. You could try to do a sort of diff and diff style interpretation where you say, well, how about the difference in effects between locations K and L by changing L's shock to have the same value as location K, that has the same problem. And then choosing arbitrary points in the shock distribution like the 25th percentile and 75th percentile also has the same problem. Okay, the math turns out identically. Now, one problem with all of these interpretations is that they're just shocking one place and thinking of the effect of shocking a single location. And we can already see in the model that what matters are the shocks to all locations. So maybe we can make some progress by thinking about the effects of all of the shocks. One way to do that is to use what statisticians call an attributable treatment effect, which says, what's the population change in this place given the true shock vector? So this is what we observe, minus what the population change in this place would have been if all of the places got 0 shock. Okay, and once you have spillovers across locations, you have to think about what's happening in all of the places. When you do that, you get, very simply, just this expression without the error term, which cancels. Okay, so that's the true effect of all shocks on the population in location L. This kind of makes clear that meaningful interpretations will involve comparisons across locations. An easy way to see that is to realize that if you take the fitted values from the regression of beta times z hat L, and you apply that to all the locations, imagine you have a shock that's negative everywhere. Some of my papers have had tariff cuts to every industry, so then the regional shocks are all negative. Well, that's going to imply population declines everywhere. But those people have to go somewhere. Okay, so that's kind of obviously problematic. So we'll do better when demeaning these shocks. That will give us the best linear prediction for the standard features of OLS regression, but the predictions are still poor in practice. We go through this in detail in the paper. The problem is that you're predicting, you're using just the shocks to this location to predict what's happening in all the migrant connected locations. And because places differ in their migrant connected locations, San Diego is connected to LA very strongly, whereas Pittsburgh isn't. We've got different shocks to migrant connected locations. And so those predictions are going to be pretty poor, even if LA and Pittsburgh face similar shocks directly. Okay. And then you'll get the same conclusion in this sort of diff and diff style analysis, but when you're thinking about the effects of all shocks compared to having no shocks anywhere. So it should be kind of obvious now, but I'm obligated to say it. Finding beta close to 0 doesn't imply that workers are unresponsive to local shocks. In fact, I can give you a very high value of theta, and if I just increase the shock correlation, I'm going to pull your beta closer and closer to 0. So it doesn't justify ignoring migration in theoretical or quantitative models. And even when you find a beta close to 0, workers may have responded to the shock you're studying quite substantially in a lot of locations. And we're going to see this in the simulations really clearly. Okay, so that's all been very negative. That's what you shouldn't do. And that is essentially what all of the papers in this literature do if they interpret beta in any substantial way at all. Some papers are quite careful to only interpret it mechanically, and so they don't fall into this. But what that also means is that you're not getting a lot of interpretation out of this regression. So what's a correct interpretation? You know, every regression estimates something. And so what does this one estimate correctly? It gives you the average difference in the effects of shocks to all places between locations facing high versus low direct shocks. Okay? So to make this a little bit tangible, consider this regression, which you can't actually run. On the left-hand side, we have that attributable treatment effect. Okay, so the difference in population growth if no place got shocked compared to the difference in population growth given the realized shocks. Regress that on the shock to that particular location, L. Okay, so we have the effect of the whole shock vector in L regressed on the one shock to L. What does B mean in this regression? It gives you the average difference in this effect of all shocks in places with higher versus lower direct shocks. Okay, that's exactly this interpretation that I've written here. Now, if you think about our orthogonality assumption, the fact that z hat is as good as random with respect to everything happening in these locations means that z hat is unrelated to the population changes that would have happened in the absence of shocks. That's often how we talk about exogeneity. So z hat's unrelated to L hat L0, which means that the estimand for B is the same as the estimand for beta, because the only difference between this regression and the conventional migration regression is that I've got this L0 on the left, but that's unrelated to the shock, so it doesn't change it. Okay? So that means you can interpret B and beta as estimating the same thing, which is this text in purplish blue here. Now, so this is what we get from beta. Is it of interest? I guess it depends on the context. It's important to remember that it only holds for the realized shock vector used in the estimation, because these are the effects of all shocks in each location. So a different vector of shocks, even with the same average magnitude and variance, if it has a different covariance across migrant connected locations, you can get a completely different answer for beta. Okay, so it's extremely dependent on the distribution of shocks that you happen to use. It depends on the context, but this estimand isn't clearly related to any of the motivations behind these migration regressions, at least as far as I can tell, although I'm happy to debate that. And as I've said a few times, you can have substantial effects in many regions, even when you get a beta close to 0. The intuition behind that is that there might not be big differences in these effects for places with high versus low direct shocks, but those places with high versus low direct shocks might have very different indirect shocks. And so any of them that have a big gap between the direct and indirect shocks will have big effects. There is another correct use of conventional regressions. And this applies to many of the papers in this literature. If you find a beta close to 0, it is approximately correct to ignore migration and spillovers when studying the responses of other outcomes, like say wages to local shocks. So I was happy to find this because most of the papers that where I run these regressions was for this reason, to see if my wage regressions were confounded. And this suggests that it's probably approximately correct. We can see that in the context of the model. The change in wage in location L depends on the shock to L, and then that will be offset by any labor supply responses, right? So of course, if you have a big increase in the wage because of a big positive shock, and then a bunch of people move in, they're going to pull down the wage. Okay, so that's why you get this negative term in front of L. And the coefficient that you would have in front of these things is the inverse labor demand elasticity, which is exactly what you want. Now, if you think about the omitted variable bias formula in this expression, but omitting L, it just depends on the correlation between the local shocks and L. And so if beta is close to 0, that means that the omitted variable, L hat, is not very closely related to the included variable of interest, Z hat. So you don't have much omitted variable bias. And that's true even if it's happening because of correlated shocks across locations. Okay, so this is a point that I want to emphasize. Not every diff and diff style regression using spatial or variation or otherwise has the problem that we're highlighting today. Wage regressions look like they're close to being okay. I'll explain that close to in just a minute. The reason that we have so much trouble with these population these population and migration regressions is that the outcome involves an individual leaving one place and going to another place. So you can have wages go up everywhere, but you can't have population go up everywhere. Okay. So I don't want you to think that every diff regression is in big trouble. Yeah, Jake, go ahead.
So I'm less familiar with these regressions, but would estimating a system of equations deal with this at all? I mean, I guess you would probably need time variation across time as well. But if I have San Diego and LA as there's some restriction on the relationship between the parameters in those two regressions based on if someone's leaving one place, they're going to the other. Is that just not how the data is structured, or am I kind of, because I'm thinking more about, demand for goods within the household. And if I'm buying more of one good, that means I'm buying less of another good. And I'm trying to make the connection with that with what's going on here.
Yeah, so I would like to think more carefully about that context. So let me not say I know the implications just yet for the consumer context. But the reason that a system of equations doesn't work here, I think, is that we're doing all of this with a long difference for a single shock. Okay, so we'll come back to multiple shocks in a minute. So if you picture your system of equations, you would just have one observation for each equation, because you've got the population change in San Diego, and then the population change in LA, and then in Santa Barbara, blah, blah, blah. Okay, and they all have exactly the same variables on the right. Okay, so this problem is best categorized as a failure of the stable unit treatment value assumption. So it's really a spillovers problem rather than an omitted variable problem or otherwise. Now, if you had lots of different shocks hitting these places at different times, and you could do lots of differences, I'm not sure that may help. I think my empiricist's response to that would be, I struggle to find one good shock in a given context in a given 50 years. And so I don't know that would be a very likely thing to happen in most of these contexts, but it's possible that you could recover similar information to what our model is going to give you if you had that kind of setting. It's a really good question. So why was I hedging slightly and saying that these wage regressions are okay? Well, first of all, the fitted values from the wage regression, they might fit kind of badly because some of these migration responses will be large in some places, even though beta is close to 0. So that's what I've been arguing, is that you can have a beta close to 0, but the gap between direct and indirect shocks in a bunch of places can still be big. It's not related to the direct shock, that's why beta is 0 or close to 0. So you might have poor fitted values in this wage regression for the same reason. And the predicted effects of a counterfactual shock might differ substantially from the true effects for places with high baseline migration shares for the same reasons that we were describing earlier. Okay, so what are we proposing? Once you've written down our model and gotten this nice expression for how the vector of shocks relates to the vector of population changes, you can simply use nonlinear least squares to estimate theta over sigma. And then you can use the estimated theta over sigma to evaluate the change in populations for either the observed shocks Z or for any counterfactual shocks that you might be interested in. Now, I emphasized at the beginning that our model is deliberately simple and doesn't include some mechanisms that you might be interested in, like say the housing market. But we're thinking of this as sort of a general proposal for how to do this sort of thing. You can, of course, write down a more complex version of this model, and this approach will still apply under some regularity conditions. So I promised at the beginning that we would talk about costly mobility across industries. And actually, this was the intuition that led to this whole project. I had moved to Pittsburgh about 11 years ago, and I was thinking about the steel bust that happened around 1981, and thinking that, I bet steel workers didn't seem nearly as mobile as they really are, because if they had a lot of steel specific skills, where were they going to go? They could go to Scranton or Milwaukee or Cleveland and work in the steel industry, but things were just about as bad there as they were here. Okay. Now, as I've read the history, it turns out things were a little more specific to the firm producing in Pittsburgh than I thought, but nonetheless, that was an intuitive idea that I think led to some correct reasoning about other shocks. And so we're going to introduce mobility frictions across both regions and industries. Now, you can just write down the same model, but reinterpret the subscripts to mean industry region combinations. And everything still holds as long as theta denotes the elasticity of switching industry region combinations. Now, the issue is that although the model can be reinterpreted at this more granular industry region level, the conventional migration regression that everyone runs is still at the location level. That's what's actually being run in the literature. And so we'll then aggregate up from industry regions to just regions. We do that for population changes, and this is an identity. And the way that this is done in practice with respect to shocks is to take shocks at the industry region level, or often just at the industry level, and then use initial industry employment shares to generate a weighted average to get your local shock. So this is the Bartik or shift share approach that you've seen in hundreds and hundreds of papers. I'm not going to go into the mathematical analysis here. You can see it quite clearly in the paper. But what we find are two important things. First, if you have a purely regional shock, then the behavior that you get from this model with industry and region frictions is exactly the same as the behavior you get from the model with just regional frictions under that low mobility approximation. Okay, so the two models should lead to identical behavior and therefore have identical problems if the low mobility approximation holds. And as we'll see, it's actually pretty close in the real world data. However, if there is an industry-based shock, as in these shift share or Bartik style analyses, there's little reason to migrate, because if you're stuck in the same industry, what's the point of moving to a new place and facing the same bad industry shock? Okay, or if you're facing a good industry shock, then it's going to be the same in the other place you might move as well. So this further depresses migration responses to local shocks. And so that will amplify the problems that we've been describing all along. Okay. So now let's move on to the empirical portion of the paper, if there aren't any questions about that. Okay, great. We're going to use matched employer-employee data for Brazil. I think the important thing to point out here is that this is an administrative census of formal employment. So it has the benefit of being all of the workers, it's the population, but it only covers formal employment. And in Brazil, there's a substantial informal sector. And so we'll lose folks that transition to informal employment or non-employment. I'll mention at the end, we've got data for a few other countries in the high income world that don't have substantial informal sectors. And so we'll be able to run the same analysis there and make sure that that's not driving anything that we're finding. We've got consistent locations over time, 486 of them in 27 Brazilian states. We've got 25 industries, 12 within manufacturing. And what makes these data great is that we can observe flows across region, cross-industry pairs. And that's sort of the limiting factor. If you want to calculate gamma and pi, or you want to calculate, forgive me for going back so far, almost there. You want to calculate Z minus L, you need to know those transitions between either locations or location industry pairs in the richer model. Okay, so that's why we're using these data in this context, because there aren't that many places where you can easily get data with transitions between local and industry pairs. So we measure gamma and pi, those transition matrices between location industry pairs. We then check to make sure that it looks like we are close to steady state using the ergodic distribution. We just multiply the transition matrices by each other over and over again, I think 10,000 times. and see whether the resulting distribution of population looks like the actual distribution of population, and it does. So the steady state assumption looks to be reasonably well justified. Here we have average mobility rates in the model, excuse me, in the data. And what we see is that industry transitions are more common than location transitions, and that there are more short distance moves than long distance moves. That's why we see more transitions between these micro region locations than between states. I should have said this before, but we're using something akin to commuting zones, but for Brazil. They're known as micro regions by the Brazilian census. Okay, so these are sub-state objects. Okay, and what we see is that low and high skilled workers have pretty similar mobility rates overall across locations and across location and industry cells. That's going to be important for interpreting some comparisons between the two groups in a few slides. So the model highlights two features of the true migration response that are missing in the conventional migration regression estimate data. The first is the local baseline migration intensity. Remember, beta uses the national migration intensity, whereas the true effect depends on each place's local migration intensity. And what you can see here is that that local migration intensity varies quite a bit. Okay, so the average is somewhere around 3 or 4%. Actually, no, it's 4.2% from the previous table. And there's a lot of variation with some places with much higher rates of migration and some places with substantially lower rates of migration. Okay, so it looks like that heterogeneity in migration shares is going to make the regression fit less well and give you less accurate predictions. Secondly, and perhaps more importantly, we're really focused on this idea that migrant-connected locations might face different average shocks depending on your current location. Okay, so this is the idea that San Diego is connected to LA, whereas Pittsburgh might be more connected to Cleveland. Okay, so we want to just see whether, in fact, migration networks are quite concentrated. We do this at the location level and at the industry level separately, and we calculate Herfindahl indices and plot the distributions of those here. You can see there's a lot of variation in concentration. To give you a sense for what the average Herfindahl across locations means, a Herfindahl of 0.165, if all the connections had the same weight, then that would be equivalent to 6 connections. Okay, now that doesn't mean that each place is connected to 6 locations because the connections can have different weights, but this just gives you a sense of the scale. And what you can see is that if we use this way to get an intuitive interpretation of the average Herfindahl, you can see that there's a lot more concentration across locations than there is across industries. Okay, because 7 out of 24 is a much larger fraction than 6 out of 485 locations. But the real point here is that there's a lot of concentration in both dimensions. So we expect that Z minus L to vary a lot depending on where you are. Okay, so we're going to use these data to try to simulate some shocks. We do that because we can ensure that the shocks are exogenous because we're simulating them, and we can vary the kinds of correlation across space to look for the problems that we're concerned about in the discussion up to this point. So we're going to draw these shocks across locations using 3 different data generating processes. The first one will be IID across locations. And this is the best case scenario for the conventional migration regression because it will mean no correlation across locations, okay, because they're independently drawn across locations. Then we'll have strong spatial correlation where we draw a shock for each state independently across states, but then we apply that shock to all of the microregions within that state. Okay, so a lot of spatial correlation. And then we're going to calculate shift share aggregates of IID industry shocks. So again, this is the best case scenario for this shift share shock. You've got a true experiment at the industry level, and then you're using industry composition of each location to get your measure of local shocks. Is that all clear? Okay. So then we'll generate the population changes according to the true model. We can do this for the model with just regional frictions or with region by industry frictions. We'll calibrate this, this ratio of coefficients or ratio of parameters, theta over sigma. We do this using numbers from the literature. We'll be running sensitivity analyses. And really, we're just trying to make the point about how these biases come in. So the particular value of theta over sigma isn't particularly important for today. Okay, so we're going to generate the data based on the model, given our simulated shocks. We're then going to take those data and then estimate beta using them with the conventional regression. And then we'll compute local population responses to both the observed shocks and one-off shocks to an individual location using beta, and then we'll compare those predictions to the true ones in the model. So we'll see how well or how badly the regression does when we know the truth, because we've simulated it through the model. So here we have the results of that exercise. So let's start with the first column and first row. So this is in the model with just location frictions, okay, the one we talked through in the first half. And then we've got IID shocks across locations. So what value do we expect for the conventional migration regression coefficient? Well, according to our decomposition of beta, we expect 2 theta over sigma, so that's 1/4. And then we know that the average migration intensity is 4.2%. We saw that on the summary stats table. Okay, so that's the share of people who migrate in a given year. And then because we have IID shocks across locations, there should be no attenuation because there's no correlation between migrant connected places. That gets you 0.0105, multiply that by 100, and you've got something very close to 0.1045. Okay, so the only reason these aren't identical is because we derived this under that low mobility approximation. Okay, but the approximation seems to hold quite well. All right, so that's what we get. We get exactly what we expect in this sort of best case scenario. Then we have IID shocks across states, so lots of correlation in migrant connected places because people tend to move more within states than across. And you can see the regression gets pulled down by almost 3/4. Okay, so the regression estimate gets much smaller in this context because of that correlation and the attenuation factor. IID shocks across industries do lead to spatial correlation in a way that relates to the migration network. So you do get attenuation, but not as much as IID shocks across states. Okay, now turn to the more realistic model where we've got location and industry frictions. You can see that with purely location-based shocks in rows 1 and 2, we find very similar coefficients across the two models. And that was the result that we had, that they would be exactly the same under the low mobility approximation. So again, it seems to hold pretty well. But look how different things are when we use this IID shocks across industries in a shift share style regressor, as does the majority of the literature. You can see that we end up with drastic attenuation compared to the world with just location frictions. And I forgot to mention, but we've tuned these shocks so that the variance of the shocks, so that the cross location variance is the same in all cases. So it's not like we've got big shocks in one case and small shocks in another, okay? The variation is the same in all these cases. So we really have trouble when we've got an industry component to shocks and industry frictions driving the outcomes. Here I plot on a scatter plot a few of these results. This is for the model with location industry frictions. On the x-axis, we have the true response in each location. So that's what we'd like to predict. And on the y-axis, we have beta times the local shock minus the mean. Okay, so where we're getting rid of that problem where we would predict positive population growth everywhere. And so you see we do okay with IID across location shocks. This is the best fit line. But for a lot of these places in the Northeast and the Southwest of this picture, we're still doing pretty badly. We get much bigger true responses than the conventional migration regression would predict. These are exactly those places where the direct and indirect shocks differ quite a bit in a way that doesn't relate very much to the direct shocks. When we move to IID shocks across industries and that shift share design, things get much worse. I mean, there's basically no relationship between the truth and the regression's prediction. This 45-degree line, this is the 45-degree line, not a regression line. And so, you know, the relationship here is really flat, as reflected by this very small coefficient that we got here. And so we've got places with really substantial true responses. Like this vector of shocks really is moving people around space a lot, even though this beta is very small. And you would predict very small changes in populations across these locations. Okay, so this is the big problem here. You can have a lot of spatial reallocation in response to the whole vector of shocks, but because your regression only looks at the direct shock, it misses all of that. Okay, now these scatter plots look a little bit silly, but that's kind of the point. If you were trying to estimate the effect of a counterfactual shock to a single location, so let's say I'm going to shock San Diego with a shock of 1, your prediction for the population change would be beta. Right, and that's how we often train undergrads to interpret our regression coefficients as well. And that's what a lot of literature does, including a couple of my papers. So you would predict the same population response across all locations if you were to shock that one location with a unit shock. So we've done that here for all of our locations and then plotted a dot for each of them with the true response on the x-axis and the prediction on the y-axis. Of course, they're on a flat line because you always predict beta. And so what you see is that with IID shocks across locations, again, you get the mean about right, but you miss all of this variation, which results from the variation in migration intensity across locations. Okay, so this is the result of missing that heterogeneity in the effects because of initial migration intensity. But when we get to IID shocks across industries, again, the attenuation is really severe. The true responses are bigger than the predicted response for all but a few places, and a lot bigger in most of the places. So we're going to think that this shock, that a counterfactual shock to an individual location would have no effect because people don't seem to be mobile, but that would be an absolutely unjustified conclusion because the effect of a unit shock to a lot of these places would have pretty substantial effects on population growth. Okay, I'm a little low on time, so I'll be brief in the next few slides. There's a large literature in labor economics finding that less skilled workers respond less than high skilled workers to local shocks. And there's a lot of concern that this leads less skilled workers to spend a lot of time in very depressed local labor markets. And it's often inferred, sometimes implicitly, sometimes explicitly, that these local workers just don't respond to shocks. Maybe it's because they don't have information. Maybe it's because their family's been in this place for generations. Maybe it's because they need childcare help and their family's all in this place. So, lots of different reasons. And those may be true. But what we've done here is given high skilled and low skilled workers the exact same responsiveness parameters. Theta over sigma is identical for high and low skilled workers here. And yet, when we take IID shocks across industries and apply them to population changes for high skilled and low skilled workers, we get huge differences across the groups. This is about half for low skilled workers of the responsiveness that you would infer for high skilled workers from this migration regression. So the only reason these numbers are different is because low skilled workers face a different distribution of shocks and a different correlation of shocks. Okay, so you can't necessarily infer anything about their true responsiveness. And why should we care about that? Well, it depends on what you might want to target with policy interventions, whether you should target retraining or moving allowances or informational interventions. So this is a very important distinction. We need to do some more work on this skill distinction. But I just wanted to
it strikes me this is a huge policy question, right? I mean, we're having sort of discussions about how to deal with sort of generations of poverty, right, among particular sort of low-skilled groups, and the narrative has been you can't get these guys to move, right? And they need, if they would just do that, we could alleviate, a huge share of kind of this multi-generational problem. So I mean, this finding suggests that it doesn't suggest it's not true, but it suggests we can't infer that from what we know. Am I interpreting that right?
Precisely. Yeah. And so we're debating in the team, do we want to make this a paper because this is such a clear policy question? Do we think the skill distinction is worth a paper? It's hard to get data to estimate what we want in the US. And actually, may I make that point in my last minute? I don't want to keep you all too late. Is that okay?
Sure, yeah.
Okay. So in brief, up to this point, the only thing affecting population changes has been the shocks. We didn't have any unobservables. And so the poor fit of this regression is really impressive when you realize that there was no error term. Okay, there was only errors because of misspecification. So I'll just blast through this. We're going to add an error term for unobserved but orthogonal labor demand and supply shocks. And then we can check the performance of our nonlinear least squares proposal. We'll do this using root mean squared error, and we'll compare it to an uninformative prediction. So what does that mean? This number 1 right here means that the conventional regression in the rich model with frictions in both dimensions when facing industry level shocks performs just as badly as guessing the number 0 population change everywhere. Okay, so that's about as badly as you could hope to perform. You can see that our nonlinear least squares approaches do much better when we use a correctly specified model. Okay, now what do I mean by misspecified here? What if the world has industry and region frictions, but you only have data on regional transitions? So you can only calculate your pi and gamma transition matrices at the location level. So you can see why we've run this, because in a lot of countries, this is the best you can easily do. And what we find is that it does quite well for IID location shocks, just about as well as the correctly specified model. But for these industry level shocks, it goes back to doing almost as badly as an uninformative prediction. So nonlinear least squares is excellent if you can get those baseline transitions at the industry location level. Okay, but the data requirements are quite substantial. So I think it's clear what we're trying to say here. We want to inform practice of people running these regressions. We think that most of the interpretations that people impose on them are inappropriate, with the exception of that confounding of wage regressions that looks approximately correct. And the source of the problem is this misspecification, because shocks to other locations matter. And the more correlated are those shocks, the more bias you get. We're going to try to add simulations for Germany and perhaps France. We have access to the data. We may consider using real world shocks to estimate theta over sigma rather than calibrating it. And then this is maybe the most important one, and then I'll stop after this sentence. Because a lot of countries don't have industry region transition data, but they do have industry transition data and region transition data. We're going to see if we can try to convolve those two matrices in some coherent way and see how nonlinear least squares does in that context, in an effort to try to reduce the pretty high data requirements that were revealed in that table I just showed you a minute ago. Thank you so much for taking the time to come to the talk and for your great comments. I'd be happy to chat more both about your research and any thoughts you have on this later on. Just feel free to drop me an email. Thank you again.
Thank you so much, Brian. I can ask one final question about migrant connected networks and their sort of evolution kind of over time. What kind of work is there on that, especially so given how?
Yeah, so I think you're anticipating something I'm excited about. Yeah, so there's one thing we can't explain and one that we might be able to explain. So there's been a steady decline in interregional mobility in the United States, if I remember right, since around the end of the 1970s. And that's just unconditional migration. That's just, did a person move? I think there's been an even larger decline in what I refer to as conditional migration, meaning the change in population given some observed shocks. Now, you could get a change in that object for all the reasons we just described. If it turns out that shocks are getting more correlated across migrant networks over time, or migrant networks have changed over time in such a way that the same vector of shocks now leads to a higher level of migrant weighted correlation, that could also explain some of those changes. And so that's one of the motivations for maybe thinking about building that skill comparison into a separate project. But is that where you were going with that?
Yes, that's super cool.
Yeah, great. I think it's potentially very interesting, but it's an empirical question.
Super cool paper, Brian. Can I ask one final question?
Yes.
I'm just thinking about this from a practitioner standpoint. I'm thinking about right, there's it did a very good job explaining there's a big gigantic suitable problem, right? How do what is the best way, if you think about just augment the conventional regression that we have, right? We have been running. What is the most intuitive way? Like, I'm thinking about like the multilateral resistant literature. You can either calculate out the resistant term or control for them, or Finster find out you can just including bunch of the country specific by year fixed effect. Like what is the most intuitive, given if like I don't have this computational power or the data to do all the great suggestions you mentioned in the paper, what is the best intuitive way to augment the regression I have?
Yeah, completely understood.
Right.
I can't give you any good answers that have lower data requirements. So for now, I can't improve on the data requirements. We are suggesting to just run nonlinear least squares. I mean, it's easy to do in Stata. That's relatively straightforward. We haven't yet proposed this in writing, but what a person could, and I'll explain why. What a person could do is just calculate z hat minus L. Because if you've got the migration flows and you've got all the shocks, which you inherently do, you can calculate z hat minus L, and then you could just control for that in the regression. If you want to take the model even a little more seriously, you could use z hat L minus z hat minus L as your regressor. That would impose the same coefficient on these two terms, which the model suggests should be true, but you could allow different coefficients and then test it. The reason that we haven't done that is that when we ran empirical experiments in the simulations using that kind of control, it performed much worse than nonlinear least squares. And so there are some aspects of this low mobility approximation that seem to do okay, like the model with and without industry frictions gets you almost the same result with location-based shocks. But there's some other dimension of variation in which this low mobility approximation is doing badly. And so I think the simplest regression-based answer would just be to control for this or use a different right-hand side variable. I still think that would be much better than ignoring it entirely. And by the way, I think it's Albert Bustos and Ponticelli. Let me see if I'm getting my citations correct. Yeah, it's this one, Albert Bustos and Ponticelli. They actually intuited their way to a control that looks a lot like z hat minus L, because they were thinking about this problem. And so you can think of what we've done partly as, at least under this approximation, rationalizing that, I think, pretty clever thing to have come up with in the absence of a model. Does that make sense?
Yeah, absolutely. Or alternatively, is that possible to do some like stack definitive to carve out better, say, controlled regions for counterfactuals instead of using all of the regions? Have you thought about that?
So I don't know how to do that with stack diff and diff. I mean, I think this relates to an earlier discussion where if you had a lot of different shocks in different time periods, then maybe you could. Yeah, okay, so if you think your shocks are being drawn from the same distribution over time, and you got a lot of them, then you could start to just ask yourself, how correlated are these shocks? Right, and then you could find the places that are very correlated and then maybe aggregate them together if that's feasible. But I think in the real world, like, do we think the Great Recession shock that was maybe based on housing markets is drawn from the same spatial distribution as the China shock? Probably not. So I don't know that you would learn much from kind of repeated empirical shocks like that. That is something for us to think more about, though. There may be something more we can do.
Yeah. Thank you.
Thank you so much, Brian. I really appreciate it. And yeah, folks can feel free to shoot him a note if you've got follow-up questions. Thank you again for your time. Really appreciate it. Really fabulous paper.
It's been a privilege, and I really appreciate all your comments and questions. So I look forward to talking with you all again soon. Thanks again.
Take care.
Have a good day. Bye-bye.